So we are talking about complex matrices. So far up to now, every matrix that we've met has been real valued. So you had something like A, B, C, D. Okay, and A, B, C, and D are real numbers. So these are real valued matrices. We haven't yet seen any complex valued matrix. We have discussed the fact that complex numbers can be represented as matrices, but those matrices are real valued, so don't make that mistake. So far we haven't seen any complex matrices. So I think we should just do a little bit of a small recap and then extension into complex matrices. There's some important terminology that we'll need to cover. So if you remember, we talked when we were discussing real matrices, we talked about orthogonal matrices. So an orthogonal matrix is one where the transpose is the same as the inverse. Okay, that was the signature of an orthogonal matrix. Okay, we also saw that, of course, that there are special orthogonal matrices where we include only proper rotations. That is to say, the determinant is +1. Okay, as opposed to -1, which are known as improper rotations. Okay, there's also the idea of a symmetric matrix. And a symmetric matrix has the property that if you take the transpose, it results in the exact same matrix as you had originally. Okay, that's a symmetric matrix. There is, of course, also something known as skew symmetric. So skew symmetric, that just means that when you take the transpose, you don't get back the original S, but minus S. So you can think of that as a corollary. Okay. Now, if we extend what we've done so far, which relates to real matrices, and we extend it into the complex realm, okay, we end up with very similar ideas but different terminology. Okay, so instead of orthogonal matrices, we have unitary matrices. So now we're dealing with matrices that have complex entries, complex elements. So A, B, C, and D are elements of complex numbers. Okay, and in that case, you have that U dagger, not transpose, but dagger. U dagger is equal to the inverse. Okay, what does U dagger mean? Well, dagger is the conjugate transpose, or the transpose conjugate. It doesn't matter which one you do first. So you must take the complex conjugate of each of the complex elements and then take the transpose. And I'll do an example of that in a minute. There is, of course, very similar to the orthogonal matrices, there are special unitary matrices which restrict the determinant to +1. Okay, and then the kind of complex equivalent of symmetric matrices are what are called Hermitian matrices. And that's where if you take the dagger of the original matrix, you get back to the original. It's the same. Okay, that's a Hermitian matrix. And then there's also skew Hermitian. Skew Hermitian is very similar to skew symmetric, so in that case you have that H dagger is equal to minus H, not H itself. Okay? Good, so what does this dagger thing mean? What is this dagger business all about? Well, if you remember that Z is a complex number, so that's A plus BI, for example. then the complex conjugate of that is A minus BI. Okay, so if I have a matrix, let's take A equal to 1 plus I minus I, 3 and 5 plus 6I. Okay, if I want to find the dagger version of this matrix, I need to first take the complex conjugate and then do the transpose. So the complex conjugate of this matrix will be, well, you take the conjugate of each element. So it will be 1 minus I plus I, 3 remains the same, and 5 minus 6I. That's the conjugate. And then the dagger, finally, would be to take the transpose of this matrix. So that will become 1 minus I, 3, 5 minus 6I. Okay, that's how that works. So these concepts and this terminology will be useful to us in the next couple of videos.